Hello, everyone. Welcome to my Data Camp tutorial series. I'm Professor Adam Kroom, and today we will focus on AI Fundamentals, Chapter 2, Supervised Learning. Go ahead and click on Continue Chapter, and I'll take you to the first video of the chapter, Supervised Learning Fundamentals. Watch the video, which will give you instructions on how to complete the next exercise, and after you've watched the video, continue to next exercise. The exercise is called regression or classification 1. Your company has a problem with too many suppliers failing to meet their delivery deadlines, which creates a lot of downstream problems in your production and many angry customers. Your boss tells you that you have a very rich database of supplier data and asks you to build an algorithm for early prediction of suppliers, which are too risky to work with. What kind of model should you use? Possible answers. Regression should be used to predict risky suppliers, or classification should be used to predict risky suppliers. The answer is classification. Exactly. You're trying to find a separation boundary between the domains of low risk and high risk suppliers, which is a textbook example of a classification problem. The next exercise is called When Regression Means Classification. Okay, so you have a classification problem at your hands. Neat. Now you talk to your client, which tells you that the algorithm needs to be implemented on their legacy systems with very poor computing resources. It turns out you can only run the simplest of models there, and you have only two options: linear regression and logistic regression. But you need a classifier, and these models have regression in their name. Can you really pull this off? If you paid attention in the previous video lesson, you know there's no reason to worry. So just go ahead and select the right algorithm for your problem. And instructions, select the right algorithm for your classification problem. So select the model, and the model we're going to use is, well, we can pick either linear regression or logistic regression. Let's go ahead and use logistic regression. And train the model. This has already been provided for us. So let's submit the answer. Good job. Not all machine learning algorithms have intuitive names, and some names are plain contradictory, logistic regression being the best example of that. Luckily, this is not the norm, but the one you just saw is usually the most confusing one. Press enter to continue. Go ahead and watch this video, Training and Evaluating Classification Models, which will give you information on how to complete the next exercise. And after you've watched the video, continue to the next exercise, which is called Spamtastic. You have built an email spam filtering algorithm. Which metric is best suited to quantify the percentage of emails your algorithm flags as spam that are actually spam? And our possible answers are accuracy, precision, or recall. And let's go ahead and pick precision. Correct. Still, you should examine recall also in order to get a sense of how many real spam emails are actually flagged as such. The next exercise is called holdout. You already know about the danger of overfitting, which occurs when your model learns the training data too well, but then performs poorly when faced with new data. Because of that, you've been urged to always test your model using data that wasn't previously used for training. But don't take our word for it, see for yourself. You will use a data set consisting of two classes. 60% of the data has been selected for training and stored in X underscore train and Y underscore train. The remaining 40% is stored in variables X underscore test and Y underscore test. You will train a random forest classifier model and see the difference in performance when it's applied on the very same data used to train it and when it's applied on data just slightly different from the training set. All right, so we've got instructions. We've got two sets of instructions. The first instruction is test the model on the same data it used for training. So to do that, let's go ahead and look on the right. We have to fill in for this. So x underscore test equals 2. Well, let's go ahead and copy and paste. Yeah, so x underscore train. Testing on training data, yeah. And then y underscore train. So I'm copying that from the left hand and pasting it right here. Testing on training data. So submit the answer. Cool. All right, next it says test the model on the holdout data set. That is the data the model hasn't seen during training. Okay, so for the first set of instructions, we tested on training data. So now we're going to test on the testing data, which is going to be different. Excuse me. And we're going to, instead of copying x underscore train, now we're going to copy x underscore test. And this is using the remaining data, yeah, 40%. So I copied y underscore test, and I'm going to plug that here for testing data. And go ahead and submit answer. Whoa, so when evaluating on training data, the accuracy reaches 97.56%, but on unseen data, it drops to 79.17%. This is a sizable difference, something you should definitely realize and solve before putting your model in production. All right, so press enter to continue. The next video is called Training and Evaluating Regression Models. Go ahead and watch this video, which will give you instructions on how to complete the next exercise. And after you've watched the video, click on next exercise, which will take you to this exercise called tailor-made. You need to estimate the goodness of fit of your regression model to your data in a relative unitless manner. Which metric should be your first choice? And we have three possible answers: the mean absolute error, the median absolute error, the R squared score. Let's go ahead and go this. Correct. Using R squared score is a nice and simple measure of goodness of fit, which all data scientists should understand and use. Cool. Press enter to continue. The next exercise is called going nonlinear. You're about to see how it's possible to model nonlinear relationships using linear regression models. To make this transition, you don't have to change anything in the model. You just have to generate higher order features and interaction features. You will first try to fit a purely linear model to a quadratic process and check the R squared score. After that, you'll use the function polynomial features to generate, well, polynomial features and see how much better your fit is, both visually and according to the R squared score. Finally, you've been provided with the custom function check underscore model underscore fit that plots the model predictions against actual data and prints the R squared score of your model. Instructions. This exercise has two parts. The first instruction is select the appropriate method to call the model training procedure. So to do that, over here, we see we've got linear underscore model dot, and we're gonna fill in a blank here, and that's gonna be fit. Yeah, select the appropriate method to call the model training procedure. Next is check the goodness of fit of the fitted model and submit answer. All right, cool. So that was correct for the first part of the instructions. The second part of the instructions asks us to use the original data set, x underscore train, to create a new data set, x2 underscore train, with second degree polynomial features. Fit the linear underscore model using the newly created data set and check the goodness of fit of your fitted linear model. Okay, so looking over on the right, it says create a new data set x2 underscore train with second degree polynomial features. So here we've got an open position, a degree equals 2. Well, we want to create second degree polynomial features. So degree equals to 2. Next, it says fit the linear model using the newly created data set. Okay, so the newly created data set, x equals 2, x2 underscore train. And check the goodness of fit of the fitted model. So to do that, we'll type right here x equals 2, x2 underscore train. And let's submit answer. Amazing, a linear model that perfectly follows a quadratic process. That is the magic trick with polynomial features. And look how easy it is to produce them using scikit-learn standard functions. Still, always make sure to understand the underlying principles thoroughly. Press enter to continue. Good job. You have completed chapter 2, supervised learning. Thank you for your attention for chapter 2, supervised learning. In the next video, I'll go ahead and cover chapter 3 of AI fundamentals. Thank you.